So we're all pretty used to what AI like ChatGPT can do, right? It's incredible. But what if I told you that the very core of these models, the thing that makes them so smart, has a hidden mathematical flaw, a kind of dead end that no amount of data can ever fix? Well, a fascinating new research paper claims it's not only found that flaw, but it's also found a way to fix it. Let's dive in.
And yeah, that's the big question, isn't it? This paper we're looking at today makes a bold claim that the attention mechanism, which is basically the engine running today's best AI, isn't just a little off. It's actually got a built-in mathematical ceiling. And that's the kind of problem you can't solve just by throwing more data or more computing power at it.
All right, so before we can really appreciate the solution, we've got to get our heads around the problem. So let's zoom in on this so-called attention mechanism, because it really is the star of the show in modern AI. Okay, so what is this thing? Well, put simply, attention is what lets an AI read a super long paragraph and figure out that when it sees the word it's talking about the car from 3 sentences ago. It's what lets it focus. It's this brilliant way of weighing which words matter most to make smarter guesses. And yeah, it's been a total game changer, for sure. But as this new research suggests, it might not be the end of the story. So, here's the kicker. The paper argues that this incredibly powerful tool has two big hidden problems. And these aren't just small bugs, they create a hard ceiling, a fundamental limit on how smart these AIs can ever really become. All right, so here are the two culprits. On one side, you've got something called the saturation phenomenon, and you can think of that as a mathematical speed limit on learning. And on the other side, there's sampling bias. This one's sneaky. It's where the AI gets so used to seeing the same old thing over and over that it starts to completely ignore rare but super important information. Let's break these down. This saturation phenomenon, it's a really big deal. The paper basically says that the math behind standard attention creates this fundamental bottleneck. It's like there's a theoretical wall that the AI just can't learn past, no matter how much data you throw it at it. It's not a computer problem, it's not a data problem, it's baked right into the math itself. And this right here, this visual perfectly captures that second issue, sampling bias. Think about it. Let's say an AI is learning about traffic. If it sees a car driving perfectly fine 99% of the time, it's going to get really, really good at predicting that. But what about that tiny 1% of the time when something totally unexpected happens? Like a tire blows out. Well, standard attention gets so overwhelmed by that 99% of normal data that it essentially learns to just ignore that crucial rare event. It becomes blind to the exceptions. And this quote from the paper, man, it just says it all. The authors say that to build an AI that truly gets the world, what they call a world model, it has to be able to separate the fundamental rules of how things work, the physics, from just how often it's seen something. Right now, our current systems just smush those two things together, and that's a massive roadblock. Okay, so if attention is broken, or at least limited, what do we do? What's the fix? Well, the paper doesn't just point out the problem. It proposes a brand new solution. It's a complete replacement for attention, and it's called the Spherical Kernel Operator, or SKO for short. So how on earth does this thing work? Well, it's a totally different way of thinking. Instead of the old method, SKO starts by basically taking all of its data and projecting it onto a single unified mathematical shape, a hypersphere. Now, the easiest way to picture this is to think of it like mapping the entire planet onto a single globe. Once everything's on that globe, it uses some really clever math to analyze all the relationships between the points on that surface. And from that, the AI can build its understanding of the world, but this time, without all the old biases. And if that last explanation was a little abstract, this analogy right here should make it all click into place. The old way, with attention, is like trying to learn a brand new, totally rigid city map for every single new task. The second you step into a different city, you're totally lost. But the new way, the SKO way, is like having one universal, adaptable globe. It doesn't matter where you are, you can always figure things out because you have this single, unified frame of reference. It's a huge shift in thinking. Okay, that all sounds amazing in theory, right? A universal globe for AI, but the million-dollar question is, does it actually work in practice? Well, the researchers didn't just stop at the theory. They built this thing and put it to the test. So, let's see what happened. What they did was set up a straight-up showdown, a head-to-head comparison. They built two AI models and made them identical in every single way. We're talking same size, same training data, the whole shebang. There was only one difference. One model used the old, standard attention, and the other used their new SKO system. And the test was simple. Which one is better at predicting the next word in a sentence? And Wow. The results are pretty darn clear. What you're looking at here is a graph of the validation loss for both models over time. Now, all you need to know is that for this metric, lower is better. The orange line is our standard attention model, and the blue line is the new SKO model. I mean, you can just see it. The blue line drops way faster and stays consistently lower. That means it's learning more efficiently and just flat out making better predictions. And if the graph wasn't enough, here are the final numbers in black and white. Look at the final validation loss. SKO is clearly lower. But then look at perplexity. That's another key measure of how well a language model performs. And again, lower is better. The baseline model is at almost 388, while SKO is down around 310. That's not a small difference. It's a decisive win for the new method. Look, this is a really big deal, and it goes way beyond just getting a slightly better score on a language test. What the authors are really getting at here is that this new approach could be a foundational step towards building what they call a true world model, an AI that doesn't just mimic patterns, but one that can genuinely understand and adapt to the world around it. So, what's the magic here? Why is SKO so much better? Well, for starters, it completely sidesteps that saturation barrier we talked about, so it can just keep on learning. It also fixes that tricky sampling bias because it learns the real dynamics of the world, not just how often it sees something. And because of that universal globe model, it can adapt to new information without needing a full, costly retrain. The paper has this great line: it learns on the manifold without learning the manifold. It's a fancy way of saying it understands the underlying structure of things without having to memorize every single detail from scratch. And all of this brings us to this final, huge question. Standard attention has been incredible. It's gotten us so far. But this research strongly suggests that it might have a mathematical ceiling, a point beyond which it just can't improve. This new foundation, this SKO idea, might just be the key we've been looking for. It could be the thing that unlocks the next great leap for AI, moving us away from models that are just brilliant mimics to AIs that can actually build an internal, flexible, and true model of our world.